This is my video number 8. So in this video I'll talk on the solution of the non-homogeneous Freedom integral equation by successive approximation. So particularly in this lecture I'll give some definition of what we mean by iterated kernel and the resolvent kernel, as well as I'll give the theorem and proof of the solution to the non-homogeneous Freedom integral equation by successive substitution, or we also say the successive approximation. Okay, so the first thing is that some definition. The iterated kernel for the non-homogeneous Freedom integral equation, we have let me write those things. Non-homogeneous Freedom integral equation is of this form. We have written this many times: fx plus lambda a to b kxt as a kernel ut dt. Okay, where fx and kx is known function, k known as a kernel of the integral, and u is the unknown function, so or the function to be determined. So the iterated kernel we define as kn xt for n 1, 2 and so on. Is defined as k1 xt as kxt. So we consider that as a k1 for the first approximation, or for the initial approximation, and kn can be written, kn xt written as integrate a to b k xs kn minus 1 st ds, for n equal to 2, 3 and so on. Or this part here, you can also be written as kn minus 1 xs k st. You just give the same answer. So this is what we call as approximate kernel or approximate function. This iterated kernel. So remember that the iterated kernel, we write k1 as the first kernel, that k, and then kn is given by this. So having this definition in mind, so we can find k2, k3 and so on. If you want to find k2, for example, k2 xt is given as a to b, if I use that definition, k xs k1 st ds, where k1 here we take from the first approximation there. And by doing this, we can have the we can define the kernel of the integral iteratively. So that's the first thing, iterated kernel. Okay, and the second thing is that the resolvent kernel. Resolvent kernel. What is resolvent kernel? So if given the non-homogeneous Freedom integral equation of that form, so the solution to that equation, let's say written as ux equal to fx plus lambda integrate a to b r x t lambda ft dt, or can also be written as ux, or fx plus lambda a to b gamma this is gamma, x t lambda, ft dt. Okay, then this r and t, remember this is the solution. This is the solution of, yeah, solution of this equation. Let's call this, let me give that solution of non-homogeneous Fredholm integrate equation, which is 1 here. So what the difference between this r and gamma? R we use for the Fredholm integrate equation, and gamma later on we use for the Volterra integrate equation. Yeah. Okay, so this r and omega, this r xt gamma and omega, this is the gamma, gamma x t lambda, we call this as a resolvent kernel. Resolvent kernel. Yeah. It looks like the same if you like the Fredholm integrate equation, and as well this. So because this is the solution to that equation. Solution means if we substitute that solution into the given integrate equation, we have a kind of identity which is left hand side must equal to the right hand side. We have dealt with those things in my first video, if I'm not mistaken. Now look at the related theorem. Theorem that related to the solution of the non-homogeneous Fredholm integrate equation, and then the solution is for the iterated kernel. So we must have the absolute and uniformly convergence. Yeah, because this you have K1, K2, K3, K4, and so on and so forth. So those series must be convergence and uniformly convergence. Okay. We have a theorem. Okay. We consider the non-homogeneous Fredholm integrate equation. Consider the non-homogeneous Fredholm integral equation. I just write that in short form. Given as ux is equal to fx plus lambda integrate a to b k xt ut dt. That's a general form of the Fredholm integrate equation. And we suppose that the kernel, the k, suppose that the kernel is different than 0 and real and continuous in the mentioned in the required region. Yeah, real and continuous in R, where R is given as this region, X in between AB and T in AB. So basically the region R is a rectangular, and also K is bounded. Yeah, K is bounded by, so KXT is bounded by some number M in R. Okay, in your notes there's some typing error. I think I will upload the edited version of the notes. Yeah, the one that I have edited. Okay, then we suppose number 2 that the function fx is non-zero, real and continuous in the interval I. Yeah, in interval I, where I is you have all x such that x in AB. Okay, this is R such that xt is given as that. And f is also bounded by some number n in R. And the third assumption we do is that the constant lambda satisfies that inequality m b minus a. So if these three condition on the kernel, on the function, as well as on the constant lambda satisfied, then the equation, this equation here, let's call this a non-homogeneous freedom integration. I put that as 1. Then the equation 1 has a unique solution, and continuous on I, as well as the form of the solution is given as ux is equal in the form ux equal to fx plus lambda integrate a to b k xt ft dt plus lambda squared integrate a to b k xt integrate a to b k t t1 f t1 d t1 dt, and so on. Yeah. So on means we have next term is lambda cube kxt integrate k t1 tt1 ft2 and so on. So let's prove this. So remember, we have three assumptions here. That's our function is continuous, our kernel is real and continuous and bounded, our function is real, continuous and bounded, and as well as the constant lambda is defined by that. Okay, so from the now to prove this, let me write the Freedom integral equation, nonlinear Freedom integral equation again. So we have ux is equal to fx plus lambda integrate a to b k xt ut dt. Now from that integral equation, the non-homogeneous Freedom integral equation, we can change the variable of integration here, or we call it dummy variable. You can change those things. It gives no different to the result. So let t equal to t1. So see what happened. So we have ux equal to fx plus lambda integrate a to b x t1 u t1 d t1. Now in the given equation, Freedom integral equation, we have ut here. Okay, you have ut. So I want to substitute this ut with that. So now we have ux, which means from that ux I can write that let x equal to t. So I can write those as a ut is equal to ft plus lambda integrate a to b, this is missing, k t t1 u t1 d t1. Okay, now if we substitute into that, so let's call this equation 1, just to make easier for us to refer. So substitute ut, this ut, into 1. You can give equation, you can give name to it if you want. Let's call that 2. Then we substitute 2. Instead of we write the name there, we substitute 2 into 1. So what we have is that ux is equal to, we have fx plus lambda integrate a to b kxt, and then ut is given here, so I can put that, substitute into there. So we have ft plus lambda integrate a to b k t t1 u t1 d t1, and then we have dt there. Then rearrange this, rearrange that. This is equal to, we have fx plus, so we have lambda kf, lambda integrate a to b kxt ft dt plus, we have here lambda squared, then integrate a to b kxt, then we integrate a to b k t t1 u t1 d t1 dt. Okay, now if we substitute this t1 u t1 here, okay, and then we apply the same approach with that. Apply the same approach means that for this I can change t1 into t2. We can change t1 into t2. Then what we have is that ut ft lambda ab k t t2 u t2 dt2. Alright, and then I can write, instead of ut, I can write as ut1 because we want t1. Let me write those things. Okay, from 2, let t1 equal to t2. So what we have is that ut is equal to ft plus lambda integrate a to b k t t1, sorry, t2 u t2 d t2, and then we change t with t1, then let t1 t equal to t1, so we have u t1 is equal to f t1 plus lambda integrate a to b k, our t is t1, t2, we have u t2 d t2. Alright, now having done this, we substitute into this equation. So let's call this equation 3. Okay, we substitute u t2. Again, if you want, you can give the name to it, equation number 4, but it's too many number of equation, so I just leave it like that. Substitute ut1, substitute ut1 into 3, So what we have, we have ux is given as fx plus lambda. We just copy from equation 3 here. Alright, so you have ux equal to lambda and everything, and this one here, and then we just substitute ut1 is given here. Okay, so what we have now, that's lambda integrate a to b kxt ft dt plus lambda squared integrate a to b k xt integrate a to b k t1 tt1 sorry t is it tt1, yeah, tt1 t1 ut1. Now ut1 we change with that, we substitute into the one that we obtained earlier. This is f t1 plus lambda integrate a to b k t1 t2 u t2 dt2, and then we have dt1 dt2. All right, so we have dt1 dt1 dt at the end. Right. Then we can rearrange this. So we have this given as fx plus lambda integrate a to b k xt ft dt, and then this term here plus we have a lambda squared integrate a to b xt integrate a to b k t1 f t1 dt1 dt, and then we have the second terms there plus we have lambda squared lambda, so we have lambda cube, and then we have these two terms here, ab kxt ab kt1, and then those things, right? So we have integrate a to b k t1 t2 u t2 d t2 dt1 dt. Okay, so again here we have ut2. We can use the similar approach as earlier, as in the previous one, where let me show you that. You can write from this one here. This is what we want, ut2. Okay, you can take first, because we don't want to get confused with t1 here already, that we already have. So what you can do is first thing, substitute this t2 with t3. Yeah, first thing you substitute t2 with t3, so you have those equation becomes ut1 equal to ft1 plus lambda integrate a to b k, we have t2 becomes t3 u t3 dt3, and then we take t1 equal to t2, so you have u t2 is equal to f t2 plus lambda integrate a to b k, this one is still t3 u t3 dt3. Alright, is that correct? So this is t3 or here T1, or T1 here, yeah, comma, so here should be T2 here, comma. And then you can substitute this into that T2, and then rearrange again. Then we have the next terms. We have one extra term. You can proceed this up to n. Yeah, if you proceed that, yeah, you have ux is equal to, yeah, proceed and then rearrange. We have fx plus lambda integrate a to b k xt ft dt plus lambda squared a to b k xt integrate a to b kt t1 ft1 dt1 dt plus so on. You have lambda cube, lambda quad, and so on up to n, lambda n, integrate a to b kxt integrate a to b k t1 and so on, integrate a to b k tn minus 2 tn minus 1 f tn minus 1 d dt n minus 1 up to dt1 dt, and plus you have one more terms here, plus we write those last term as Rn plus 1 x, yeah, where Rn plus 1 x is given as lambda n plus 1 integrate a to b kxt integrate a to b kt t1 kt t2 and so on, and last term integrate a to b k tn minus 1 tn minus 2 kn minus 1 kn minus 2, we should written t, oh yeah, just tn, sorry, tn, we have d tn dtn minus 1 and so on. We have dt1 dt. So that's our Rn. Okay, now we have shown that the solution to our integral equation, yes, solution to our non-homogeneous Friedel integral equation here can be written as that. So what we need to show now is that does the series on the right hand side of that f1 fx plus everything here, does this series converge? Because this, if it not converge, then the solution is void, it's meaningless. So therefore we need to ensure that, or we need to show that this solution, the on the right hand side of that solution is converge. Now we consider those on the right hand side of that equation there, ut. So on the right hand side we have fx, yeah, that right hand side. Here we have fx plus everything there. So consider fx plus lambda ab kxt ft dt plus lambda squared a to b kxt integrate a to b kt t1 f t1 d t1 dt dt plus and so on. So we consider that series. Okay, now from the assumption in the theorem that we have, where is it? Okay, here. From the assumption of the theorem you have, the modulus or magnitude of k is bounded, f is bounded, as well as our lambda is given by that. So what we have, and as well as each of these function k real and continuous, f is real and continuous. If you put it here, you can see this is a continuous, this is a continuous, this continuous. All of these are continuous. So therefore, our solution or our series, this series here, let me give this name. We have 1, 2, 3, 4. Let me call this series number 4. Okay, so therefore we have since this kxt fx are continuous. This is from our assumption, yeah, from our assumption of the theorem. Therefore we have those series 4 series is continuous. Okay, now we need to show the convergence with the the convergence, yeah, convergence. Now in order to show that, so we let the general term of that equation, let's denote that as tn x. Let's call the general term of those, which is lambda n integrate a to b k xt integrate a to b k t1 and so on, plus integrate a to, this is not plus, multiply, a to b k tn minus 2 tn minus 1 f tn minus 1 dt n minus 1 dt minus 2 and so on, dt1 dt. Okay, which from there we can take the absolute value of all those things, and since this is just a multiplication of those functions, yeah, we multiply with that and then we integrate, it's just, you can split those things one by one, lambda n and so on. Those you can take out that kxt and so on. And then from the theorem, that 1, 2, 3 here, k is less than, k is bounded by m, f is bounded by m. So what you can see, and as well as we have lambda by that, so we can have this thing is less than, we have n m nm, we have n b minus a over n. Okay, so let me check the derivation. Just 1 minute. Yeah, so we have lambda n here. Okay, so in order to ensure that those series converge, in order to show that this is converge, what we need, to ensure for converge, we need those lambda m b minus a, we need this less than 1. So why? Because when those base is less than 1, you increase the power, is getting smaller and smaller, so it's basically approaches to a small number. So what we have here is that lambda less than 1 over m b minus a, and this is in line with our assumption in part 3 here, lambda less than that. So if we have this, and we show that we also can have that, then our solution to the non-homogeneous Freedom integral equation has a unique solution, continuous and as well as converge. Okay, so does the series the infinite series converge absolutely and uniformly when the condition holds? And you can also show that the R, this part here, you can show that if you take a limit of those, n goes to infinity, Rn plus 1 x, this, you can show this is equal to 0. So which means somehow this solution has a finite number of terms. Finite number of terms. So this is the proof of those theorem. So I think with the definition of the iterated kernel, what is the resolvent kernel? So resolvent kernel, I gave you basically one for Freedom integral equation, and the other one is for Volterra integral equation. And I also proved that the theorem, the solution to the non-homogeneous differential integral equation is unique and continuous, and as well as converge for the successive method. So therefore I stop here for this video. We'll meet in the next video on how to solve given a particular Freedom integral equation, and we will develop the method how to solve it using a successive approximation or iterative method, and then we give you example of how to do that. Okay, so with that, I thank you. See you in the next video. Bye.